Hey, so I'm Joseph, and this is the second part of the third chapter of Stewart's Calculus, and we're going to be talking about optimization. So optimization is basically an application of the concepts learned in the previous chapter, so like figuring out extreme values of a function. It's the application of that technique in calculus to other problems, basically problems where you have a couple possible values, you have some constraints, and you want to find the maximum or minimum of some combination of those values. And that's like really nebulous, but really all we're going to be doing in this video is going through some different kinds of problems with optimization that appear in your book and elsewhere that you're going to be needing to solve. So first we're going to look at question 15 on page 257 of your book. Alright, so if we've got a 1,200 centimeters squared of material to make a box with, and it has a square base and an open top, so that means only 5 sides because a cube generally has 6, so 5 sides. You want to find the largest possible volume of the box. So this means that the 4 sides around the base can be rectangles, but the base has to be a square. There's no top, and and the total surface area is going to be 1,200 centimeters. So let's write that down. So surface area is going to be 1,200, and let's kind of draw a diagram of the box. So we've got, that's one side, and we've got this square base right here. And each side of the base is going to be the same value because it's a square. We can call that x. And then the height can be something else. We'll call that h. And so the volume of this is going to be all 3 of these values multiplied. So it's going to be x squared h. There you go. So this is most of the stuff we can glean right away from the problem. But let's go back to the other screen to start solving. Alright, so here's this information, and remember, our goal here is eventually to use some function for the volume and find the maximum volume. And so we've got our 2 equations here, something with surface area and something with volume, and eventually we're going to need to relate the 2. But first we should probably get an expression for the surface area in terms of the dimensions of the box. So we're going to have 4 sides like that. So that's going to mean that we will have surface area and 4 of these sides, which the area of which is going to be h times x. So we have 4h times x and only one base, because remember, open top. So plus x squared. So that's a general formula for the surface area, and that surface area needs to still equal 1,200. So eventually we want to be maximizing this equation of v. However, v is in terms of 2 variables right now, x and h. And since it's a single variable calculus, we only know how to differentiate, which is what we need to do in order to maximize. We need to differentiate this with respect to one variable. So we need to put this in terms of one variable. And we could do it with respect to either, but I'm going to put it in terms of x. And so since we have this other equation, we can get an expression that puts h all in terms of x. So let's find that expression. So we can take an x, we can kind of factor out an x here. So that would make this x times x plus 4h, and that'll be equal to 1,200. Divide this x over, and so we'd get x plus 4h equals 1,200 over x, and then we can subtract this x and divide everything by 4, and so we would get h equals 1,200x minus another x all over 4. So that is our expression of h. And now what we're going to want to do is we're going to want to plug this h in for that h in the v equation to make this all in terms of x. So to get v in terms of x, we'll get the x squared, and then that previous expression, we're going to plug it in for h, and that is going to be a fourth 1200 over x minus x. There we go. And so we can do a little bit of simplification here. We can multiply this x squared into this equation to make this a little bit more manageable. And so that'll be a fourth 1200x minus x cubed. And now we can start doing our optimization. Really, optimization is just a fancy word for finding the maxima or the minima, and in this case we're trying to find the maximum volume of the cube described, or not the cube, the prism described by these dimensions. So the first step in finding the maximum or the minimum of something is taking the derivative of it. So first let me put out that equation for v in terms of x that we just found. Now, first step, take the derivative, so that would be v prime of x, and so this is all with respect to x, so this is nice and easy to solve. We bring this 1/4 in here, we get 300, and so the derivative of that would be 300, because 1200 divided by 4 is 300, minus, so that would be 1/4, so we bring the 3 down, that would make it 3/4 x squared, oops, that's an ugly 4, 3/4. And since we're trying to find the extreme value, we want to figure out where the derivative is 0, and then make sure that at least one of those values is a maximum, because that's what we're trying to find. So we're setting that all to 0. Now, what we can do is, got 300 equals 3/4 x squared. We can bring that all over. Multiply by 4, divide by 3, that'll make it 400 equals x squared. And so, and you square root this, we'll get either plus or minus 20 equals x. So those are our extreme values, and now we need to figure out which one of those is a maximum, or maybe both of them are maxima. Alright, in order to to figure out which one's a maximum, we're going to use the concavity test, or the second derivative test. So we're going to take the second derivative of v prime prime x, and that 300 will go away, and we will bring this 2 down, and so we'll get negative 3/2 x. And so we're going to try to plug in for positive 20, v prime prime 20. And remember, the one that's a maximum, this value is going to have to be less than 0 in order for it to be a maximum, right? Because then that would mean it's concave down, and the point resting on top is relative max. Alright, is negative 320, and that would be negative 30, and that is less than 0, so yes, that is a place where v is going to be a max. That's a value of x where v is going to be a max. And we're still going to want to test negative 20, because that could also be a max. We could have 2 maximum points. It's just always a good idea to check both values. So that would be negative 3/2, negative 20. And we can already see that this math is going to work out where those 2 negatives cancel out. So if you're on the AP test and you see that, don't continue doing algebra. You can just figure out that that's going to be greater than 0, and it will be a minimum value. So, this is one thing to be cautious of. The question asked, what is the maximum volume, not where will the maximum volume be. If it asked you where it would be, you could say, well, when the value of x is 20. But no, it asked you what the maximum value is. So you're going to actually need to go back to that original v equation and plug in 20. There you go. So that's that original equation for the volume in terms of x, with 20 plugged in for x. There you go. And this will all work out to 4,000. And add units. In the question it was in centimeters squared, so we'll continue with those same units. So that'd be centimeter cubed. And that right there is the max volume, and that is one of the applications of optimization that you're going to have to be familiar with. Now, let's say I go on to one that's a little bit different. Alright, so this is the next problem we're going to do, and it's problem number 35 on page 258 in your book. And this is a pretty common problem for the AP to give you common optimization problems. So, we've got one piece of wire that's 10 meters long. So we know we're going to have some total length equal to 10. And it's cut into two pieces. One piece is going to be bent into a square, and the other is going to be bent into an equilateral triangle. How should the wire be cut so the total area is a maximum and a minimum? So that's not too much extra work to do both of these, so we will do both of them. So basically what we've got is we've got a square and a equilateral triangle. And let's say the perimeter of the square is x, and the perimeter of the triangle is y. Then we'd also have 10 equals x plus y. Now, and so this is just about all that we get from the problem directly, and we can extrapolate some more later. So we've got some length equals 10, and that 10 is equal to the perimeter of two different things. Great, so let's go over to the other screen and start solving for this. Alright, so this is what we've got so far. We've got our square and our equilateral triangle, and so ultimately we're trying to find the maximum area that can be enclosed by both of these. So we're going to need expressions for the areas of each one of them, which means we're probably going to need to use their dimensions. So if the perimeter of the square is x, and each side of a square is the same, each side can be represented by x over 4. And equilateral triangles divided by 3, each side can be represented by y over 3. And that's how we can define those dimensions right there. And now we're going to need to get expressions for the area of each one, and that's pretty easy. If we use the formula for the area of a triangle, we get, and so I'm just going to call that a sub x will be equal to both sides times one another, and that will be x squared over 16. And for the area of the y, you might not remember the formula for an equilateral triangle. You can do some trig work to figure it out, but when you plug it all in there, ay will equal root 3 over 36 times y squared. And remember just conceptually how that all works. You figure out this value here, you multiply it by one of the bases, divide by 2. That's how you get the area of a triangle. And so now we can say a total, so the area enclosed by both of them, the expression for that is going to be ax plus ay, and that is x squared over 16 plus root 3 over 36 y squared. So now we have our expression for area, and we also have this expression in terms of length, because same with the previous problem, this area, which we're going to need to maximize or minimize, optimize is the general word, we're going to need to take the derivative of it, and we can't take the derivative of it with respect to two variables. We need to put it all in terms of one. So we're going to kind of use this equation up here as a constraint. So it doesn't really matter which variable you try to put a into in terms of. You could put a in terms of y or x. It's basically the same amount of difficulty, because this equation will give you kind of the same thing either way. But I'm going to put it in terms of x. So we're going to get an expression where y is in terms of x. So 10 minus x equals y. And then we're going to plug that into here. So that would be a equals x squared 16 plus 3 over 36 times 10 minus x squared. Alright, yeah, and then we do a bunch of algebra to simplify this out, and this is about the simplest that we're going to get the equation of a in terms of x2. There you go. So now we're going to be able to optimize, which means taking the derivative and figuring out at which value of x it will be 0. Alright, so now we're going to take the derivative of this, so we're going to try to get a prime of x. And actually, we can take this root 3 out of here. And the only thing that disappears is going to be over there. That constant's going to disappear. And then, yeah, we got 1/4 9 plus 4 root 3. And then this 2 comes down, so the 36 becomes an 18. X minus, and then that stays over 9, and then that disappears. So that's the derivative, and we're going to figure out where, for what value of x, it is 0. So now we can put this 1/4 in here, and we will get, and so we can put this all over the same denominator, actually, which would be, put it all over 18. So that'd be 9 plus 4 root 3 x, that is all the coefficient, minus, and then in order to do that we need to multiply, put a factor of 2 in there, minus 40 root 3 all over 18 equals 0, and so that would mean we would get 9 plus 4 root 3x over 18 equals 40 root 3 over 18, and these 18s will cancel out. Oh, and both sides are multiplied still by 1/4. And actually, yes, that 4 also would end up canceling out on both sides, so we can ignore that. And then we can divide down that coefficient over here, and we will get x equals 40 root 3 9 over 9 plus root 3. And that is the one extreme value. Now we can analyze this in terms of maxima and minima. Alright, so now we can take the second derivative of a to figure out what kind of value x is. So take that's a prime prime of x, and really all that's going to be is this coefficient over the 18 divided by 4. And so that will be 9 plus 4 root 3 over 52. And so this is a constant. The second derivative is a constant, and that's greater than 0. So when you plug x into there, that is going to make x a place where the area is going to be at a minimum value. And so I'm going to plug that in later, but remember we also need to figure out where it is a maximum value. And so how are we going to do that? Well, we can analyze endpoints. So, and generally you'd have to figure out where the endpoints would be on this. Figure out, like, okay, how big can this, what's the limit of how big the square can be, what's the limit of how small the triangle can be, and really that limit is 10 and 0. If x is 10, that means all of the wires being used for the square. If x is 0, that means all the wires being used for the triangle. And yeah, and so, but the thing is we don't have, or alright, we can, well, all you need to know is, okay, so the limits of x are going to be 0 and 10. So if we get a of 0, based on that previous equation, we will get the first two terms are 0, and then it will be 100 root 3 over 36. There you go. And a of 10 will be that plus some other constants, plus 1 with an x squared in the in it, and I mean a 10 squared, 100 times one factor, and then subtracted a little bit. But what you have to know is that when x equals 10, that's where there's going to be a maximum. Also, you know this because there's a parabola, there's an x squared in the term, in the equation. So the maximum value of the total enclosed area is going to happen when x equals 10. And so this is all the work that we need to do for this problem, because the problem, if you remember, said where should we make this cut in order for the maximum enclosed area or the minimum enclosed area to happen. It doesn't say what that area has to be, so all you have to do is figure out x equals 10 and x equals that term. Say one's a minimum, one's a maximum, and you should be good. So yeah, stay tuned for the rest of chapter 3. It's also pretty interesting. Thanks.